Hello, welcome to 3612 Ida Bell Lane. My name's Nathan. I'm one of the builders of this project, and this video is all about how we got this house airtight. If you want to know why we got the house airtight, there's a whole other video dedicated to that, which is pretty nerdy and gets into the weeds, but hopefully fills you in and makes you feel good about airtight construction. So this video is all about the construction details that we put into this place to actually do that. If this is the first video that you're seeing as part of the series, just know that there's a whole other playlist about this house that gets into all the different ways that we went above and beyond to make this a higher performing building. So check all the rest of that stuff out. For now, let's get into the air barrier discussion here and how we did it on Ida Bell Lane. First thing, starting from the ground up, we have a conditioned crawl space. That gets the mechanical system to the inside of conditioned space, which is really important for reasons that I explained in the other video. And it gives us the ability to seal at the foundation. That keeps the outside out of our crawl space. It keeps the crawl space from getting outside. We have a rigid foam insulation on the walls. We have a sealed plastic vapor barrier all across the dirt. And then we transition up into our floor system from there. When we make that transition, as we built the floor frame, we first started by laying a gasket down in a bead of sealant on top of the foundation so that that flat piece of wood called the sill plate that rests on the foundation and then carries the floor joists on top of it was sealed to the foundation. We then built the floor, we built the walls. Okay, the walls are sheathed in Huber's zip system sheathing, which you can also learn more about in the water management video because that layer doubles as two things: our water management layer and our air control layer for our exterior walls. So the transition from foundation to sill plate, the sill plate to the floor frame, and the floor frame to the walls happens at that zip system sheathing. That is a 4x8 panel that's airtight and waterproof, and it's all taped together with a flashing tape that sticks for the life of the building. So that's how we got the wall surfaces air sealed, okay? At the base of the wall, where it connects to the foundation, we ran a bead of really high quality sealant all the way around the perimeter of the house. That's continuous. And that seals the wall system back to the foundation of the sill plate that we talked about just a second ago. Okay, now what about holes in the wall system? Okay, there are, I guess, a couple of main types of holes that we had to deal with when it came to the way the walls went together. And those are the big obvious ones like windows and doors. And those are the little ones like wires and pipes and so forth that may penetrate to the outdoors. At the window and door openings, we made sure to use Zip Systems tape all the way around the opening to connect that sheathing to the wall framing. And that was important because the window or the door that goes into that opening has to be integrated into the air barrier. And so it's not going to touch the sheathing in ways that we can seal. Like, for example, in the water management video, you'll hear me talk about the way that we left the bottom edge of the windows untaped on the outside. So we've got to figure out how to get the sheathing to connect to the inside of that window frame. And the way we did that was by wrapping the tape into the framing of the rough opening, install the window, and then we connect the window to that framing using a canned foam sealant all the way around. Same thing on the doors. So there's no joint that can leak at the sheathing to framing interface because that's taped. There's no joint that can leak between that and the window because that's foamed, and that's how we handled our window and door openings. The utility penetrations like wires and pipes that stick through the wall, those were handled with a gasket product that we found that I really like. I talk about this in the water video as well. But to run it down again, it's an EPDM gasket. That's the same rubber that they use for rubber roofs, the black kind. There's other kinds that are different colors. But it's a really robust product, and it comes from the factory, you know, pre-punched to the hole of different sizes depending on what size thing you want to seal around. And in some cases, it was actually integrated with a piece of really high quality flashing tape all around the edges, so that all you had to do was slide it over that line and then tape it back to the zip sheathing. And now that penetration is air sealed. Really, really cool. I love too how those things allow you to reposition the line or maybe even like fully remove and replace the line and not lose that airtight seal that we've got around those things. So that's the wall system. Now, We have our air barrier on the outside of the walls in the form of the sheathing, but when we transitioned to the ceilings, we actually brought the air barrier to the inner surface of the framing there. And the way we did that was by building the wall and pausing the framing process for about a day so that we could run a membrane all across the tops of the walls with all the little pieces of membrane kind of connected together in advance, so that when the roof and ceiling framing went in, we didn't have all of these annoying breaks to contend with in that air barrier transition from outside to inside. So that piece of house wrap lays out across the tops of the walls. On the outside, it's folded down and taped to the zip system sheathing, and then on the inside, after all of the framing was done, after all of the wiring and plumbing and duct work and everything was complete, we were able to then cover the rest of the ceilings with more of that house wrap product, tape it all together, and now we have one just big monolithic air barrier that wraps from the bottom of the house, up the walls, and then across the ceilings. And that's how, in general terms, we got airtight here. Now, some more details about how we handled some of the penetrations through the ceiling air barrier in this house. Number one, the lights. All the lights in the ceilings are surface mount LEDs. We don't have any of the big, recessed cans going up through the ceiling like you may have seen before. But all of those light fixtures need a wire, and they need an approved housing for that electrical connection above them. And so those were a bunch of holes that we had to punch in our air barrier that would have been really hard to seal, except for the way that we handled those penetrations, and that was this. We built a whole bunch of boxes out of scrap leftover pieces of OSB. We taped all of the corners of those boxes together, and then we mounted those boxes up in the ceiling at pre-planned locations wherever there would be a light, so that whenever we ran the house wrap on those ceilings, wherever we came to a box, we were able to just simply cut the box out on the interior side and then tape that house wrap up into the box all the way around. And that's how we transitioned our air barrier up and over those light fixtures and connection boxes, so that we only had one hole to seal wherever there was a light, and that was for the wire that comes in through the side of that box to power that light. That was a way more effective air seal than trying to somehow deal with all of the contours and knockouts in those electrical boxes. I'm not so sure I would do that again, honestly. It was kind of a lot of hassle. But it worked well enough here that we got a really good result on the air tightness test that we did at the end of construction. So that's the light fixtures. The other things that penetrate the ceiling are the bathroom exhaust fans. And that's something I want to take a minute and talk about too, because this is actually really important. The bathroom exhaust fans are contained within airtight enclosures of their own. Similarly to the OSB boxes that we built for the light fixtures, we enclosed the bath fans in a box, but it's not OSB, and it was built around the bath fan afterward, and it's made of rigid foam board. That was how we got the bath fan itself into an airtight enclosure, because to have sealed the fan housing would have been really tough. There's all these like holes in the sheet metal that those fans are made of, and the penetration through the drywall is kind of hard to get to and really effectively seal. So that's why we did the box. So we built a box around the fans, and then we taped the air barrier membrane up into that box. But the most important thing that we did for those bath fans is an upgraded backdraft damper. We have seen before in my work diagnosing building failures where mold will grow on a bathroom ceiling in the immediate vicinity around that fan. And that's because of backdrafting. You'll have hot, humid air in the summertime working its way backwards through that pipe that bathroom fan is supposed to blow out of, getting past the factory damper in that bathroom fan and out into the room below. And as it creeps out of that fan housing and kind of trickles across the ceiling, it creates an elevated humidity condition on that drywall that in many cases is sufficient to allow for the growth of mold. And that's something that we wanted to prevent here. It actually happened at my personal house a couple of years ago, and it was very embarrassing. That's cared for now, don't worry. But we wanted to make sure that we didn't turn over a building to you that was going to have that same issue. And so we used an upgraded backdraft damper here. It's called the Fantech RSK series. And I really love them because they are a gasketed damper with a very light spring that holds a couple of butterfly flaps closed when the fan's not running. So any backdraft pressure cannot open those flaps, but when the fan is running, they open up all the way, and it works really, really well. I have tested homes, I have tested dampers. The factory damper on most of the bathroom fans that are sold in North America is actually designed to stay slightly open until a certain amount of pressure comes against it. And I'm not exactly sure what the reason for that is. I'm sure I could, ask the tech people at the fan manufacturers, and they might have a reason why they do that. But I have found that if you go check out the why we want to air seal video, I talk about stack pressure and I talk about mechanical pressure. I have found that the light amounts of pressure generated by the stack effect, or in some cases the mechanical systems of a house, can actually backdraft those fans without getting so high that it makes that damper shut. And so that's a real problem. And that's why we want the upgraded backdraft dampers on this house, so that, number one, we've cared for it by having a really good air barrier. We've cared for it by putting the mechanical system inside of conditioned space. And so between those two things, we have greatly lowered the potential for pressure on those bathroom exhaust fans. But there's always going to be some, and so that's why we put that damper on there as an extra measure of defense. The kitchen range hood, the clothes dryer, these things can create negative pressures in the building that might otherwise allow backdrafting at those fans. And so now with the dampers that we put on them, we're protected. That was way more than I thought I would ever talk about backdraft dampers, but hopefully, hopefully I'm communicating to you that we really thought a lot about what we did here. And what's amazing about those dampers is that they're only $15. It's a $15 part, okay? You pop it on there, it takes 10 seconds. Really not hard to do at all. But it's something that's gonna save you a lot of hassle down the road. It's gonna prevent that condition for mold growth that I talked about, that I've seen in other homes, and it just made sense. So anyhow, that's all that. Now, as far as how airtight we got this place, we scored a 1.4 on the blower door test. Okay, I'm about to explain what all that means, okay? The blower door is an apparatus, an instrument, a device that we use to measure air leakage in a house. So the idea is that you run the fan up to a standardized pressure level. So all buildings are tested at the same pressure level. And at that test pressure, you measure how much air is flowing through that fan. Now, the whole 1.4 thing that I just talked about a second ago is the outcome of that test. So the unit of measurement for air tightness that kind of prevails in North America is ACH 50. That stands for air changes per hour, and 50 refers to that test pressure, and that's 50 pascals. Pascals is the unit of measurement for the pressure. 50 is the quantity of pascals. That's the standard test pressure that we were testing all of our buildings at. And so ACH 50 is air changes per hour at that 50 Pascal test pressure. When I say air changes per hour, what I mean is how many times in the course of 1 hour will all of the air mass of the building be completely evacuated and replaced? How many times will it change over? Okay, air changes per hour. 1.4 is awesome, okay? It is really stinking good. To put this in perspective, the legal requirement in our area right now is 7 air changes per hour. In other words, your building has to have 7 air changes per hour or less on the blower door in order to pass building code minimum requirements. In the state of Georgia, that's 5 air changes per hour. And that's not even actually on the most recent version of the building code. But the house that we are standing in right now is 5 times more airtight than the current legal requirement. That's awesome. Let's say that our jurisdiction were to update to a more recent version of the code. The next strictest, or the most, what am I trying to say here? They've only made that stricter one time. So the code books are updated about every 3 years. The most recent version of the code book is 2024. The energy code that governs airtightness that is currently in effect in our jurisdiction is the 2018 version, but believe it or not, we actually amended in the requirements from the 2009 version. And so that's why we're on 7 air changes per hour in our area. The 2012 version of the code and onward changed that 7 to 3. As I said, we're on the 2018 version, but we amended in the requirements from 09. And this was an effort to make building easier in our area. But even if we were on that new version of the building code that requires 3 air changes per hour, this house at 1.4 is still more than twice as good as that. So we're really happy with the air tightness level that we've achieved here. And we made sure to do it in ways that were achievable. Like, we didn't use anything fancy. We didn't do anything especially complicated. It was just a few small steps at certain phases of construction that we added into the process that, you know, added maybe a couple of days to the course of the build. It really wasn't much at all. The extra materials were very affordable, and you know, it involved a lot of scrap. It involved a lot of affordable selections like the house wrap instead of the European stuff. And I think the results are really great considering how relatively easy it was to do here. And I want to make the point that we did it without the use of spray foam. Okay, we'll talk more about that in the insulation video, but you know, one of the biggest arguments in favor of spray foam is how much more airtight it can make your house, and it can, but it's not the only way to get there. And we did that here without needing to do that. All right, well, I think that's about all I need to say about airtightness here and how we did it. Hopefully you've enjoyed the explanation, and we thank you for checking out this video. Click around to the other ones in the series if you're interested in more information on the other systems of the house that we've tried to upgrade here for a better outcome for the living experience and the overall health and durability of the building. Thanks for watching.